Today is the 6th lecture of this course and the 4th lecture on the topic of equilibrium carrier concentration. What we did in the last class was that we tried to give a qualitative model for this particular data that we had shown in the beginning of this discussion on the topic. What we did yesterday, we could write in the form of an equation Ni is equal to capital N into P power E by kT, where N is the atomic concentration in silicon, P is the probability, that an atom is hit by a particle, okay. E is the bond strength and kT is the average energy of the particle at temperature T under equilibrium conditions. So E by kT represents the number of particles that must converge onto an atom so as to provide an energy E equal to the bond strength, okay. So the entire discussion that we did can be summarized in the form of this equation. Now here P, the probability is less than 1. So if we were to write this equation using 1 by P here so that we get a quantity more than 1, then we can correlate this equation very well to the behavior that we have shown. So the same thing written in terms of 1 by P would be it would look something like this. Now it is very clear, if I take log of Ni, I will get that is equal to log of N minus E by kT into log of 1 by P. 1 by P is more than 1, so log of this quantity would be positive, okay. So according to this, log Ni is proportional to minus E by kT. So therefore if you plot Ni on a log scale and 1 by T or reciprocal of temperature on the other axis, that is the x axis, so log Ni is plotted on the y axis and 1 by temperature is plotted on the x axis, then I will get a straight line. This is exactly what this slide shows. Now here the differences between the straight lines associated with silicon, germanium and gallium arsenide can readily be associated with the changes in E for these three materials, where E is the bond strength, E 1.1 electron volt for silicon, for gallium arsenide it is 1.42 electron volts and so on. Thus the qualitative model is quite good in predicting the behavior. What is the problem here is that we do not really know what is this P, we have no way of calculating P in the model. So what we can get is a broad behavior, okay. We cannot make accurate calculations, but we can definitely show, or rather we have shown using this model that Ni on a log scale varies as reciprocal of temperature, and the behavior is linear when we plot log Ni versus 1 by T, which is not a small achievement at all, okay. To get a more accurate description where we can make calculations at any temperature, we must go to the band model, which is the topic of discussion today. Actually the band model means the energy band model. Many times the word energy is dropped. The energy band model. The energy band model, what it does is it tries to analyze the electron population in terms of the energies possessed by electrons. So more specifically what we are trying to do in this is to see how the electrons are distributed over a range of energies at any given temperature. If we have some way of finding out this distribution, then we can very easily separate that part of this electron population which is free and that part which is bound at any temperature, okay. So the basic tenets of this model are three. The first one refers to the allowed energy states for electrons. Electrons are only allowed certain energy states. They are not allowed all energy states. This is the first important principle of quantum mechanics, you know that. So only certain energy states are allowed. Second, of the allowed states, the electrons tend to occupy always the ones with lowest energy which are available. So electrons occupy the lowest energies available. Lowest energy states available. And third, which is the Pauli's exclusion principle, it says that no two electrons can occupy the same energy state. So this is the first important tenet of this energy band model, that is the allowed energy states. Now next, how many states are there and how these allowed states are distributed over energy. So distribution of allowed states over energy. This distribution is represented using a function n in brackets E, that is n is a function of E. That is to say that all the states which are available for electrons to occupy are not necessarily distributed uniformly over energy. Okay? So what is the exact distribution, that we will have to see. What is the distribution, what is the function Ne? Now the third and the last important tenet has to do with what fraction of the allowed states are occupied at any temperature. The fraction of states that are occupied at any temperature and energy. So electrons will not occupy all the states, okay? Only a fraction of the states will be occupied, which obviously means the allowed states are very large in number, much larger than the number of electrons. Okay? So that is why the question arises, how are these states occupied? So at any temperature under equilibrium condition, this is where the condition of equilibrium is coming. Under equilibrium, only a fraction of allowed states are occupied. And this fraction is written as f of E comma T. This fraction is a function of the energy and a function of temperature. This is normally called the Fermi-Dirac function. This function is derived from statistical mechanics. So while the function Ne, the distribution of allowed states over energy, is obtained from quantum mechanics, and the first principle of allowed states also is a statement of quantum mechanics, the last tenet or statement, this particular thing is related to statistical mechanics. So the energy band model combines results from statistical mechanics and quantum mechanics and tries to put them together, okay, in a coherent form. So now let us take up each of these three tenets one by one. What are the allowed states for electrons in a crystal? Okay. Then what is the distribution of these allowed states over energy, and then what is the fraction of these states that are occupied? The allowed states. So what we do here, if we start with the picture associated with an isolated atom, we will take silicon as an example. Isolated silicon atom, what are the allowed energy states? Then you put together n atoms, all regularly arranged, and then you start reducing the interatomic distance between the n atoms and bring it down to the distance that we have in the crystal, and that is the way you try to see how the allowed energy states picture for an isolated atom progressively gets modified, okay, and then we get the picture for electrons in a crystal. So if you were to follow this approach, if I were to sketch on a diagram like this, where the x-axis denotes atomic separation and y-axis denotes available energies or electron energies. How will this picture look like? Okay. So let me build up this picture. We are trying to plot it for an n atom system. All n atoms are regularly arranged. You start with very large or infinite separation. When the separation is infinite, each atom is isolated, although it is still an n atom system, but still in effect one atom is isolated from the other atom. So that therefore we are starting with the picture for isolated atom at this right extreme. Okay. Now you know that silicon, the atomic number is 14. And the distribution of these 14 electrons is written as 1s2, 2s2, 2p6, 3s2, 3p2 in terms of the various orbitals. Now you plot energies corresponding to this. So 1s2, that is the energy of an electron that is very close to the 1s orbital, is very close to the atom. Okay, and progressively these correspond to energy states of electrons away from the atom. Okay. So on this particular diagram, the lower energies will correspond to electrons close to the atom, and the higher energies will correspond to electrons away from the atom. So if I were to show this, it would look something like this for an isolated atom. Okay, we are not taking an atom system, you take an isolated atom, then it would be something like this. So the highest is 3p, so this is say 3p, then below that you have 3s, then you have 2p, 2s and 1s. Here I must mention that this diagram, the distance between the various energies is not necessarily to scale. Okay. So 1s, there are two available states. If you strictly use the Pauli's exclusion principle, those two states of 1s orbital should be shown separately. Okay. Similarly, if you take for example this 2p orbital, there are 6 states, all the 6 states should be shown separately. Okay. But then if you do that, the diagram becomes complicated, so we use some simplification. What we assume is that for simplicity, both the states of 1s orbital are at the same level. So I can show that by using 2 circles here. A circle corresponds to a state, and I will cross this circle to indicate that this state is occupied. So 1s2, then comes 2s2. So you have 2 states available and both are occupied. Then comes 2p6, so there are 6 states, so 1, 2, 3, 4, 5, 6, and all 6 are occupied. Repeat that here, 3s2, 3p, there are 6 states but only 2 of them are occupied. Okay. Look at this, 3p, only 2 electrons are there in this, although there are 6 states available. In any p orbital there are 6 states, so 1, 2, 3, 4, 5, 6. So I will cross some 2 of them to show only these 2 are occupied. So this would be the distribution of the 14 electrons in an isolated silicon atom over various energies. Okay. Now here I have shown a line, which means that over a range of atomic separation we are assuming that this holds. Okay. Again, this is strictly not correct because you are slowly bringing the atoms closer. So we are assuming very high energies, very high separation. So in order to indicate to have some simplification in the diagram, we can assume that for very high separations the picture is the same. This is a picture for isolated atom. If you have n atom system, the only modification that will take place here is for every atom there are 2 electrons. For every atom there are 2 electrons, and since each atom is isolated from the other atom, the 2 electrons of all the n atoms in the 1s state would be at the same energy. So instead of 2 electrons now, the picture here is 2n electrons, and if you proceed like this, here for this 3p state there are 6 n states available for an n atom system. All the 6 n states are at the same energy in our simplified model because the atoms are isolated. However, out of this only 2n states are occupied. Okay. So you just multiply this number by n. So this is 2n states and 2n electrons. You can go on writing similarly for this. I will write for this end and for the other end. Here you have 6n states but only 2n electrons. Okay. Now let us see what is going to happen as you bring the atoms close. As you bring the atoms close, the coupling starts between the various atoms, and now you again apply the Pauli's exclusion principle. Since no 2 electrons can have the same state, each energy state is going to split into n states. Okay. When they are far apart, this issue does not arise because there is no interaction between them, but once the n atoms start coming closer, there is coupling, and no 2 electrons in any system can have the same energy, so there will be small changes in energy of each particular state. So as a result, what happens is this 3s states, as you bring the atoms closer, will tend to spread into a range of energies. So that is what is shown here by spreading of a single level into a band. Strictly speaking, in this, for example, band, there are 2n states and 2n energies, so I should show 2n lines, separate lines, something like this. But since the n is very, very large, in silicon, for example, we know that 5 into 10 power 22 atoms per centimeter cube. This is a very large number. So these various levels will be so close to each other that we can almost regard them as a continuous, forming a continuous band. So we do not show the levels as discrete in this, it is as though they are spreading into a band. So similarly, same thing happens here. So it tends to spread into a band. Now what is important to note, that the energy levels corresponding to electrons which are very close to the atom, for them the effect of the other atoms will come about only for very low atomic separations, because they are shielded by the other electrons. So in terms of our energy band diagram, what it means is that even though these outer levels are getting influenced by other atoms and therefore they are spreading into a band, the inner levels here will not spread into a band so easily by this atomic separation. So you can simply show this as a discrete level at this stage. Now if you proceed further, reduce the atomic separation further, it turns out that calculations indicate that these two bands merge for some atomic separation, and if you go down further, you have a single continuous band, and you reduce the atomic separation further, this continuous band spreads into exactly two bands, two different bands, and this is how the picture looks like, okay, for lower and lower atomic separation. For this particular 2p level, the spreading begins only here, and for 1s level it is even later. So this is electron energies. So what does this mean, this diagram? Let us concentrate on these two because those are of interest to us. In fact, the 4 valence electrons that we talk about are these 4 electrons in the 3p orbital, okay. So in this case there are not 4 but 4n electrons. And how many states are involved? If you take this third orbit, this particular level, 3p and 3s together, total number of states involved therein are 6 plus 2, 8. So what it means is the 6n states here are spreading and the 2n states here are spreading, and they are merging together over this region. So in this region, that is over this atomic separation, you have 8n states, but only 4n electrons, because out of these 6n states only 2n are occupied, okay. Out of these 2n states all 2n are occupied, but here they are merged, so there are only 4n electrons. Now this is where what will happen is, out of the 8n states, the 4n electrons will occupy the lowest states available, okay. In other words, if you were to do a similar exercise for a metal, you will find that the metal crystallizes in this atomic separation range, okay. What we have drawn is for silicon. You can draw a similar diagram for a metal. Then for that metal also you will get a similar behavior, where you will find the crystal, the atomic separation in the crystal will be in this range. That is why you have a continuous band of which only a part of energies are occupied. But for semiconductors, for example in silicon, it turns out that the crystal, in the crystal, the atomic separation is here, okay. What is it that decides the atomic separation in a crystal? What is the interatomic distance? What should be the interatomic distance in a crystal? This is decided by the fact that all the attractive and repulsive forces should cancel, the lowest possible energy, okay, total energy. Now if you use that criteria and find out the atomic separation, it will turn out to be somewhere here for silicon. Now this shows why at this atomic separation in the crystal you have one band separated by another band, okay. So this is the gap, these energy levels are not allowed. Further, calculations indicate that the number of states in this band are exactly 4n, and number of states in this band are also exactly 4n. So 4n states, and here in this band also 4n states. But total number of electrons we know is 4n in these 8n states. So all the 4n electrons will occupy this lower energies available. So the upper band will be empty at t equal to 0k if there is no energy provided to the electrons. So here you have 4n states and 4n electrons. 4n states and 4n electrons. Here 4n states but no electrons. This band is the so called valence band, because all the valence electrons are occupying this energy band, and this band is the so called conduction band, because when you provide energies to the electrons jump from the valence band to conduction band, and when they jump, the electrons which are in the upper band are free to move, so therefore they are called conduction electrons. Now what is of interest to us in analysis of semiconductors is just the band picture at this atomic separation. So here let us write this, that this is the atomic separation in a crystal. So what we are interested in is only the band picture along this line, that is of interest to us. So just that part of the picture we can draw. It would look something like this. So on this axis you have electron energy, and now you do not have to show anything on this axis, because we are bothered only about the band picture at the particular atomic separation. Okay? So this is a band picture, the particular atomic separation. So this is one band of allowed energies, then energies are not allowed in this band, then again you have another band of allowed energies, then you have really very small width of a band, or almost a point. So this point corresponds to 1s, this to 2s, this is 2p, this is the band corresponding to 3s and 3p, which are merged and again separated, and this is also the band corresponding to 3s and 3p, which are merged and separated. Okay? So this is the conduction band. This is the valence band. We are not yet explained why the electrons which are in this band can participate in conduction. That is something we will do later. Now only we want to, I just want to tell you what is the name assigned to these bands, that is all. So this allowed band is conduction band, this allowed band is valence band, and this difference is energy gap. Now it turns out that the lower energies are not of interest to us, because most of the properties of the semiconductor can be understood in terms of these two bands. Okay? And therefore one does not show these lower energies. Further, it is of interest to note on this diagram which is the energy corresponding to an electron at infinity, that is totally separated from a crystal. That energy is somewhere here. Note that this entire range of electron energies indicates that range which corresponds to electrons within a crystal. So you want to have a reference. What is the energy of an electron which is removed from a crystal and which is moved totally away from the influence of atoms? That will be somewhere here. This level is normally referred to as vacuum level. Vacuum level or vacuum energy level. So in practice now it is somewhat difficult to work with a diagram like this, wherein the endpoints, the ends of this band are indicated as points. So what one does is, for simplicity, instead of a point you draw a line. Okay. So the representation that we will use for explanations would be something like this. So vacuum level will be drawn as a line, and this level, the symbol used is E suffix 0. Okay. So this is the vacuum level. And then the conduction band will be shown using two lines. The lower level of this will be represented by the symbol E suffix C. C stands for conduction. The valence band will be shown below this, and the top of this band is denoted E suffix V. V stands for valence, and this gap is denoted E suffix G, energy gap. As we will see, this represents the bond strength of the bond model, energy corresponding to the covalent bond. Now this gap between E naught and EC, the difference between E naught and EC is called electron affinity, usually denoted by the symbol chi, Greek letter or alphabet. So electron affinity, and this is energy gap. So that is the conduction band, and this is the valence band. So please note that when the levels are drawn in this manner, the x axis here does not indicate distance. You should not think that this indicates distance, okay, because as we have said, strictly speaking, this is the correct diagram, because you are drawing the allowed energies at a particular separation. So here you should only have a point, but as I said, it is difficult to work with this diagram, so you are just drawing it like this. Instead of saying that the level is a point, it is very difficult to show a point, so you draw a line. Okay. So these are electronic energies. E stands for electronic energies. Now before we leave this topic of allowed levels, let us try to understand why is it that when the electrons, when the atoms come closer, an energy level of an isolated atom splits into different energies. Okay. When you have coupling between various atoms, then the energy levels corresponding to the various atoms split, they are not the same. This is a very important point that one must note. It comes up at several places in sciences. Okay. The splitting of energy level because of coupling between the systems or elements of the system. So we will illustrate this with an example of an analogy. So what is shown here is a spring mass oscillator. Okay. So we will first have a discussion related to this oscillator, and then I will indicate to you how the situation here is analogous to the situation that we have discussed for electrons in a system. Okay. So supposing I were to set this oscillator into oscillation, it will have some frequency of oscillation which is given by 1 by 2 pi into root k by m. K is the spring constant and m is the mass. Now these three oscillators are independent, they are not coupled in this case, there is no coupling. So what happens if I try to set 2 into oscillation, it will have the same frequency as the first oscillator. I can set 3 into oscillation, it will have the same frequency. Now supposing I were to couple these oscillators by coupling spring as shown in this blackboard. So we introduce a coupling spring something like this, so that the oscillators are coupled. Now what would be the frequency of oscillation of this system? So let us look at the frequencies of oscillation for this 3 oscillator system when they are coupled. So one particular mode in which the 3 oscillator system which is coupled together can oscillate is this mode that is being shown, where all the 3 masses are oscillating in unison. In this case the coupling really has no effect, this frequency is the same as the frequency of an isolated oscillator. But now this is not the only mode in which the system can oscillate. For example, it can oscillate as follows: the center mass is stationary and the left and the right mass are oscillating in opposition. Note that the frequency of oscillation is now more than the frequency of oscillation when all the 3 were oscillating in unison. Why? Because now the effect of the coupling spring is also coming into picture. Effectively the k has increased, the spring constant k has increased, so your frequency is more. Compare it with this oscillation. Okay, this is slower. So this is the second mode of oscillation. There is a third mode in which this particular system can oscillate, and that is the center mass is oscillating in opposition to the outer 2 masses, and outer 2 masses are oscillating in unison. Okay, this frequency is even higher than the previous frequency where the center mass was stationary. Okay, so let me play the 3 modes again. This is one mode of oscillation. This is another mode of oscillation, a higher frequency, and this is another mode of oscillation, an even higher frequency. So a 3 oscillator system has 3 different frequencies when the oscillators are coupled. The 3 oscillator system has 3 different modes of oscillation or frequencies of oscillation when the 3 oscillators are coupled. One can easily extend this argument logically, and if you put an n oscillator system, you can show that it will have n different modes of oscillation and n different frequencies. Okay, now let us come back to our discussion here. In the oscillator analogy, the oscillator is analogous to atom with a single allowed energy level. Further, the natural frequency of oscillation of the oscillator is analogous to the allowed energy level. That is the value of the allowed energy level. And finally, the coupling spring is analogous to the interatomic forces. That is the forces between one atom of silicon and the other atom of silicon. So if you look at the analogy in this particular way, then we will easily understand how a single energy level splits into more energy levels equal in number to the number of atoms which are getting coupled. Now we will also understand that if in the oscillator, for example, if this coupling spring is very strong, if you increase the strength of the spring or the spring constant K, then the three different frequencies, that is F0, F1 and F3, for the three modes of oscillation of this particular system, the separation between these three frequencies will go on increasing. So now you have F3 is the maximum frequency, then you have F1, then you have F0. If you go on increasing the coupling strength of this, the coupling between two oscillators or the strength of each of these individual springs, then the difference between F0, F1 and F3 will go on increasing. The separation between F0, F1 and F3 will increase. Similarly, if you bring the various atoms close together in a system, then the coupling between the atoms increases or interatomic forces increase, and in that case the separation between the various levels which have arisen from a single level, that is the single level is splitting into n different levels for an atom system, the separation between these levels will also increase if the atoms are brought closer. Or in other words, if all these levels are very close, then the separation of a single level into energy band, the width of the band will go on increasing as you decrease the interatomic separation. That is what we saw in our allowed energy level versus atomic separation diagram. So now let us summarize our energy band diagram. We come back to this diagram that we have drawn. E0 is the energy level, that is called the vacuum level. EC is the edge of the conduction band, lower edge of the conduction band. EV is the higher edge of the valence band. This EG, difference between EC and EV, is the energy gap. This is equal to 1.1 electron volt for silicon. And this chi, which is electron affinity, difference between E0 and EC, is equal to 4.05 electron volts. So actually, if you draw this band diagram to scale and try to show the conduction band and valence band, then it would look something like this. This is E0, this is EC, and this is EV. So for silicon, this is about 4.05 electron volts, this is electron affinity. This is the energy gap, and this is 1.1 electron volt. And now if you try to show the bands, the valence band would be about 5 electron volts, something like that. So 5 times this, so your valence band would be this much. and similarly you will also have a wide conduction band, something like this. So you see that the energy gap is really small as compared to the width of the band. This is how the diagram looks when you draw it to scale. So wide allowed energy bands separated by a very narrow energy gap. It is always good to look at a diagram to scale, because then we know the magnitudes, the relative magnitudes of various parameters. Now let us see the correspondence between the band model and the bond model. The various events which are taking place in the bond models, such as generation and recombination, how do they look like on the band model? Now an electron breaking the bond and becoming free to move about within the crystal, it undergoes a change in energy as shown in the band model. So this is the process of generation in the band model. On the other hand, the recombination process, that is a free electron jumping into the vacancy and getting annihilated and establishing a bond, this is recombination. On the band model it will look something like this. So here what is shown here, the dot represents electron and the circle is hole, the electron has jumped into the hole. So this is recombination, the electron jumping from conduction band to valence band. Now what about an electron gaining energy? A free electron gaining energy, more kinetic energy, its velocity is increasing, it is remaining within the crystal. This is equivalent to an electron jumping up in the conduction band. It is gaining energy. On the other hand, a vacancy or a hole gaining in energy, how will it look like? A hole gaining in energy is the same as the valence electrons or bonded electrons which are moving through the vacancies gaining in energy. So this is equivalent to the valence electrons gaining in energy or electron moving up in the valence band. You can also show this process as a hole moving down. So either an electron moving up in the valence band or the hole moving down, because when an electron jumps up in the valence band, the hole which was there here comes down. So this is hole gaining kinetic energy, and this is electron gaining kinetic energy. Now finally let us look at another important transition. An electron jumping up let us say from valence band to E naught. What does this event shown on the band model represent? This is equivalent to an electron remaining within the crystal but taking part in a bonding process such as this. So this is a bond. An electron, there are two electrons, one associated with this atom and the other associated with this atom, they are participating in a covalent bond. Now if this bond breaks and an electron is set free but moved out of the crystal, so the electron is coming out of the crystal, then its energy transition would be represented as shown here. From electron is jumping from valence band to the vacuum level. Now it is important to note here that whether the electron is on the surface here or far away from the silicon crystal, the energy of these two electrons is the same, because both these electrons are out of the influence of the atoms. This is true only if the silicon piece is uniform. So therefore the question arises that an electron which is at the vacuum level, where is it? Is it here or is it here? In our semiconductor physics, normally we take the electron to be on the surface. There is a reason for this, which will become clear when we discuss non-uniform silicon blocks or p-n junctions and so on. So this transition here represents an electron moved out of the crystal, but the electron is localized on the surface of the crystal. So that is why this E naught is referred to as the local vacuum level. So if the electron was a free electron, then the transition would be something like this. So a free electron moved out of the crystal is equivalent to this transition. Now in the next class we shall discuss the remaining two tenets of the band diagram, namely the density of states function, how the allowed states are distributed over energy, and then what is the fraction of these states that are occupied at any given temperature and energy. That is the Fermi-Dirac distribution function or the Fermi-Dirac fraction.